Okay, in contrast to the Cauchy-Schwarz inequality, where you needed some clever idea like using the quadratic formula to finish the proof, the triangle inequality is very straightforward to prove. You just use the Cauchy-Schwarz inequality at a key moment, but the consequences are very, very valuable. So let's look at this proof. Again, we're going to use the idea that the magnitude of a vector squared is equal to the dot product of the vector with itself. So let's consider the magnitude of u plus v squared. It's equal to u plus v dotted with u plus v. And then we use the idea again from rule number 2 that we can expand the dot product here as u's dot u plus u dot v plus v dot u plus v dot v. And the u dot u is mag u squared, and the v dot v is mag v squared. In the middle, u dot v and v dot u are the same, so I have 2 copies of that. Mag u squared plus 2u v dot product plus mag v squared. But now I use the Cauchy-Schwarz inequality. This number, u dot v, has got to be less than or equal to the magnitude of u dot v, or the absolute value of u dot v, excuse me. Because if this number is positive, these two are equal. If this number is negative, this is less than that. So that means I can say certainly that I could replace this with this, and I'll be no greater than, I'll be certainly less than or equal to mag u squared plus 2 mag u mag v plus mag v squared. A little bit sloppy with my magnitude bar, sorry. But this is a perfect square. This is mag u plus mag v squared, quantity squared. So look at the 2 beginning and end. This is a positive number being squared. This is a positive number being squared, non-negative numbers at least. That means if I take the square root of this side, it will remain less than or equal to the square root of that side. Mag u plus mag v. And now we've proved the triangle inequality. What does this mean in plain English? In plain English, it brings geometry to third dimension, higher dimension. It says, really, that if you travel in a straight line, that is shorter than any other path, sum of 2 vectors that's not in a straight line. So the shortest point, the shortest path between 2 points is a straight line. Okay, that's kind of not mathematical, but colloquial. But that's the basis of building geometric figures. Also, let's look at this. What would happen if u dot v was 0? That means this is a right angle. That means this is a right triangle. So let's pretend u dot v is 0. What do you see what it says then? The length of the hypotenuse is equal to the square of the length of the leg plus the square of the length of the other leg. It literally says that if u dot v is 0, then mag u plus v squared is equal to mag u squared plus mag v squared. That's the Pythagorean theorem. But notice that's the Pythagorean theorem in 2 dimensions, 3 dimensions, 4 dimensions, any dimension. I'm not talking anywhere about the number of slots I used in this proof. That's irrelevant. So now I have standard geometry that the shortest distance between 2 points is a straight line, and the Pythagorean theorem. And from here, I have the concept of angle in second dimension, third dimension, fourth dimension, any dimension I please. Finite dimensional. If I want to go to infinite dimensional, then you have to do some other accounting. Okay, famous inequalities, Cauchy-Schwarz inequality and the triangle inequality.